Good morning students, this is lecture 3 under module 11, and as you know that we are discussing about the commodity chemicals from biomass. Today we will discuss about precisely 3 very important commodity chemicals, 1,3 propanediol, 2,3 butanediol and then PHA. So, let us begin. We will start our discussion about 1,3 propanediol. 1,3 propanediol can be used as an essential monomer to synthesize a new type of polyester, that is polytrimethylene terephthalate, very well known as PTT, and as an ingredient in other polymers, cosmetics, foods, lubricants and medicines. 1,3 propanediol is a 3 carbon diol with hydroxyl groups at 1 and 3 carbon positions, that is why the name is 1,3 propanediol. It is one of the oldest known fermentation products, described as early as 1881 by August Freund in the glycerol fermenting anaerobic culture containing Clostridium pasturinium. Having 2 functional groups, 1,3 propanediol is a high value specialty chemical in polymer synthesis, in particular as a monomer for polyesters, polyethers and polyurethanes. For instance, polyester associated with 1,3 propanediol exhibits unique features such as the elastic recovery of nylon and superior stretching, which are difficult to obtain from other glycerol based products. 1,3 propanediol has been produced mainly from petroleum derivatives such as acrolein using hydration and hydrogenation catalytic reactions, the well known Degussa dew point route, and ethylene oxide using the hydroformylation and hydrogenation catalytic reactions, the well known Shell route. Now, in addition to the chemical catalytic processes, DuPont and its collaborator Genencor International have developed the glucose 2,1,3 propanediol biological process. After an extensive effort was undertaken to make metabolically engineered Escherichia coli. So, Genencor is a well known company which manufactures different types of enzymes. Okay. So, what they have done is that they have metabolically engineered the E. coli, and both DuPont and Genencor have developed the process of making 1,3 propanediol using a biological route from glucose. Considering problems with the conventional chemical process for the 1,3 propanediol production. So, those are petroleum based material for sources, high pressure and temperature in processes, as well as environmental aspects caused by the toxic chemicals and the intermediates. The fermentation based 1,3 propanediol production as an economically competitive chemical process has been recognized as one of the novel biological processes, representing a paradigm shift from the petroleum products to biomass based renewable products. So, this is actually true for all other chemicals which we have been discussing since last 2 classes, that due to the problem mostly environmental problems, okay, then the depletion of the fossil based resources, there is a need to look for biomass based platform to develop or produce such platform and commodity chemicals. So, considerable attention has been paid to 1,3 propanediol production other than from glucose, especially glycerol, because it is a huge amount, as you have been discussing many times, and you will recall that glycerol is one of the most important byproduct from the biodiesel processing unit. Only 10% has been used for some value addition, rest is a waste. Okay. So, there is a huge demand to make the glycerol as a value added product. So, a large amount of raw glycerol is generated, okay, in the range of almost 10% wet by wet biodiesel during the production of biodiesel. Unlike the chemical conversion of glycerol to 1,3 propanediol, the biological conversion of glycerol to 1,3 propanediol is an environmental friendly and economical process due to the low energy requirement with mild reaction conditions compared to that of high chemical processes, because in chemical processes you go for higher temperature pressure, okay. And there is also a higher yield of 1,3 propanediol than that is achieved by the chemical reaction. That can be one of the most significant result of this biological route. Now, 1,3 propanediol can be produced naturally under anaerobic as well as microaerobic conditions by various microorganisms, including the genera Klebsiella, and then Clostridia, Enterobacter, Citrobacter and Lactobacillus group. Now, this is the classical general metabolic pathway of the glycerol degradation. So, we can see that how it actually happens. So, we can start with glycerol there. So, this is the usual route to produce butanol, acetate, ethanol, etc. Okay. from the glycerol. Now, if we go for a dehydration reaction, then glycerin will result in 3-hydroxypropanaldehyde, and that upon degradation will give us 1,3-propanediol. Okay. This is the route. Now, this is the standard route of metabolic pathway, okay, through which we get many different types of products. So, glycerol is getting converted to phosphoryl pyruvate, then to pyruvate using these particular steps, okay. Then pyruvate to lactate, otherwise pyruvate to straight away to acetyl coenzyme. Okay. Similar thing we have discussed during our fermentation pathway discussion. Okay. Now, acetyl coenzyme again goes back to acetoacetyl coenzyme, and this pathway will give us N-butanol as well as butyrate. Now, acetyl coenzyme also can be converted to acetyl to acetate, acetaldehyde to ethanol. Okay. This is the usual route for the ethanol. Now, a pyruvate also can convert it to acetone and 2,3-butanediol. So, I hope you will understand that with glycerol itself only we will getting so many different types of products, but having said that, please note that all these products, whatever components, okay, the chemicals that is being generated or produced from glycerol using this metabolic pathway are not in an sufficient quantity. Okay. So, their concentrations will vary, okay, and some will be in higher concentration, some will be extremely low concentration, that it is very difficult to purify. Now, having said that, metabolic pathway can also be engineered in such a way that you can target to produce 1,3-propanediol, you suppress this particular route. Okay. Those technologies are already established and it has been done. Suppose you do not want 1,3-propanediol, you can directly suppress this, you can go for any one of this. Okay. If you suppose you want ethanol, we can try to suppress this particular route. Okay. There will be some production of N-butanol butyrate, but we need to suppress the route. Okay. Similarly, any one of the product. Okay. So, in addition to 1,3-propanediol, the genera Klebsiella can produce ethanol, 2,3-butanediol acetate, and Clostridia can produce butanol, butyrate, ethanol and acetate. Now, we just saw that from glycerol we can get so many different products, but what are the products and all that again depends upon the type of species that you are using. The best known 1,3-propanediol producing wild type bacteria to that belongs to the genera Klebsiella and Clostridium, because of their high tolerance to 1,3-propanediol and their high yields and productivity. So, other bacteria such as Clostridium fruendi, Lactobacillus brevesi, Clostridium pasturinum can also produce 1,3-propanediol, but at a relatively low concentrations as well as low productivity. There are two important enzymes involved in the 1,3-propanediol synthesis in Klebsiella pneumonia. So, one is glycerol dehydratase, okay, which is written as GDTH. So, it is vitamin B12 mediated dehydration, that is the route, converting glycerol to 3-hydroxypropanaldehyde, and then the next enzyme is 1,3-propanediol oxidoreductase PDOR. Okay. What it does? It reduces 3-hydroxypropanaldehyde to 1,3-propanediol. Okay. Subsequent steps. Now, the accumulation of the 3-hydroxypropanediol, a microbial precursor of the 1,3-propanediol, has been known to inhibit 1,3-propanediol production because of the toxic effects. Now, the next class of the commodity chemical is 2,3-butanediol. 2,3-butanediol is also of commercial interest as an anti-freezing agent due to its low freezing point and as a feedstock for the formation of methyl ethyl ketone by dehydration, which can be used as a liquid fuel additive. 2,3-butanediol is a 4-carbon diol with hydroxyl groups at 2 and 3 carbon positions. This compound is also known as 2,3-butynyl glycol, 2,3-dihydroxybutane or dimethyl ethylene glycol. Now, 2,3-butanediol has a high boiling point of 177 degrees centigrade and a low freezing point of -60 degrees centigrade. So, the LEVO form of 2,3-butadiene basically, and is a promising anti-freezing agent. Now, there are 3 different stereoisomeric forms of 2,3-butanediol, okay, 1 plus, D minus and a meso form. So, you can see this, these are the 3 different forms. Okay. So, this form is the 2,3-butanediol, it is the LEVO rotatory form, and this is L plus 2,3-butanediol, this is dextro rotatory form, and this is the optically inactive form. Okay. 2,3-butanediol is an industrially useful chemical with numerous applications in the manufacture of printing inks, synthetic perfumes, softening and moistening agents, a solvent for resins and lacquers, and a carrier for drugs and pharmaceuticals. Furthermore, the derivatives of 2,3-butanediol such as methyl ethyl ketone, okay, and 1,3-butadiene have attracted much attention recently because those chemicals which are now produced by a petroleum refinery process can be produced from biologically produced 2,3-butanediol. Methyl ethyl ketone can be produced from 2,3-butanediol by dehydration. It is a simple process, okay, and it can be used as an effective fuel additive because of a higher heat of combustion than ethanol. An interest in 1,3-butanediol butadiene production from 2,3-butanediol increased significantly during World War II, because 1,3-butadiene is an essential monomer for synthetic rubber. In addition, 1,3-butadiene can be converted to styrene by dimerization, okay, which is an important aromatic building block for polymer. Due to the shortage of fossil fuel supplies and rising oil prices, the biotechnology for the production of 2,3-butanediol has received much attention recently. Numerous microorganisms have been known to produce 2,3-butanediol from a variety of carbohydrates such as glycerol, hexose and pentose, as well as lignocelluloses through a microbial fermentation processes. These include a number of species of the genera Klebsiella, Enterobacter, Bacillus and Lactobacillus. Klebsiella oxytoca and Klebsiella pneumonia are facultative anaerobic bacteria which obtain the energy for growth and maintenance through aerobic respiration and anaerobic fermentation. The Klebsiella species is also found to utilize various substrates including glycerol, glucose, xylose, mannose, galactose, arabinose and lactose, making it feasible to produce 2,3-butanediol with cheap substrates or low cost substrates such as biodiesel waste, lignocellulosic waste, etc. Usually 2,3-butanediol is synthesized as a mixture of two isomer types of 2,3-butanediol by different microorganisms. For example, Bacillus subtilis can produce the D form and mesoform in almost equal amounts, whereas on the other hand Bacillus polymixa, okay, or polymixa produces only the optically active form of 2,3-butanediol. There are only a few reports on stereoisomer analysis of 2,3-butanediol produced from different microorganisms. Now, during the fermentation, microorganisms produce 2,3-butanediol along with other byproducts such as ethanol, lactic acid and acetic acid. It is crucial to use all of the available cheap substrates for the cost effective production of the biofuel and bio based chemicals, because the cost of raw material significantly influences the final cost of the product. Wood and agricultural biomass, mostly the lignocellulosic materials, are popular candidates for low price biomass resources, and there has been an increased interest in research on their use for 2,3-butanediol production. Among components in lignocellulosic materials, cellulose is a polymer of glucose and hemicellulose contains hexose and pentose. According to previous results, 2,3-butanediol can be produced from various types of carbohydrates including hexose and pentose sugars, which are liberated from lignocellulosic materials by hydrolytic method. Each hexose and pentose or mixed substrate has been examined for 2,3-butanediol production. Among them, glucose has been the substrate most often examined for 2,3-butanediol production. Aerobacter aerogenes NRRL B119, this is the strain name, okay, yielded 0.45 gram of 2,3-butanediol per gram of glucose at the initial glucose concentration of 195 grams per liter. Then Bacillus polymixa utilized glucose as a carbon source for the production of 2,3-butanediol. The inhibition of growth occurred at substrate concentration exceeding 150 grams per liter. These are very classical studies, the references are given, you can browse through later on if you are interested to read more into detail. Bacillus licheniformis produce 2,3-butanediol from glucose when grown either in air or under nitrogen. After 72 hours of fermentation on a 2% weight by volume glucose at pH 6 and 37 degree centigrade, the optimum yield of 2,3-butanediol was 47 gram per 100 gram of glucose. In addition to glucose, the use of various pentoses and hexose has been examined for 2,3-butanediol production. Janssen and Sao reported that Klebsiella pneumoniae was able to utilize various pentoses including xylose, arabinose, mannose, galactose and cellobiose for growth and 2,3-butanediol production. The maximum specific growth rate of 1.05 per hour occurred at a xylose concentration of 20 grams per liter, okay, by Klebsiella oxytoca under aerobic conditions. Janssen and et al. Performed a 14 batch fermentation for 2,3-butanediol production and simulated 2,3-butanediol production with respect to the oxygen transport rate and initial xylose concentration. With an initial xylose concentration of 100 grams per liter and an oxygen transport rate of 0.027 mole per liter per hour, the average 2,3-butanediol production rate was 1.35 grams per liter per hour. The production of 2,3-butanediol from lignocellulosic wastes other than purified hexose and pentose has been considered as an economical method. Laube et al. Attempted to use acid hydrolyzed aspen wood, larch wood and oat spells, but only a low 2,3-butanediol yield was obtained even with the additional xylose, implying that there was an inhibitory effect of hydrolyzate on 2,3-butanediol production. Okay. As we know that beyond certain concentration, all the products as well as substrates can inhibit the entire fermentation process. So, that care must be taken. Okay. Fraser and McKenzie investigated the effect of the selected components in acid hydrolyzed hardwood on 2,3-butanediol production by the Cleblis pneumoniae species. According to their results, sulphate up to 0.2% weight by volume and furfural up to 0.2% again weight by volume did not affect growth, but sulphate reduced 2,3-butanediol by 30%, while furfural induced growth slightly. So, phenolic compounds including syringaldehyde and vanillin significantly inhibited growth as 2,3-butanediol production as low as 0.1% and 0.05% respectively. So, both these components syringaldehyde as well as vanillin are great inhibitors in the entire fermentation process to produce 2,3-butanediol, okay, using this particular strain. Okay. Grover et al. Used wood hydrolysate after neutralization with calcium hydroxide and filtration. In flask cultures, 2,3-butanediol was produced at 12 grams per liter with a yield of 0.27 gram per gram of sugar. Glycerol is also considered to be a cost effective and efficient carbon source for the production of 2,3-butanediol. Then Cleblis pneumoniae DMS 2026 has been known to be a 1,3-propanediol producing strain as well as a 2,3-butanediol producing strain using glycerol. This is what we have already seen when we discussed at the beginning of our class about the 1,3-propanediol production. So, this Cleblis pneumoniae GT1 produced 2,3-butanediol from glycerol at low pH and microaerobic conditions. When the pH was lowered stepwise from 7.3 to 5.4 in a continuous culture, 2,3-butanediol formation started at pH 6.6 and reached a maximum yield at pH 5.5 under microaerobic conditions, while production of acetate, ethanol and 2,3-propanediol decrease. So, this is what we want. I was just talking if you recall during our discussion during metabolic pathway. So, if you want to maximize 2,3-butanediol production, then you have to suppress the production of other components, whether it is acetate, ethanol, 1,3-propanediol or any other such components like even butanol also. Okay. So, while this Cleblis pneumoniae can produce 1,3-propanediol and hydrogen only under strictly anaerobic condition, the microaerobic conditions caused little 1,3-propanediol production as well, but higher 2,3-butadiene production in the presence of oxygen and glycerol. That is a very interesting study. Fed batch culture of this particular strain was carried out by Petrova and Petrova by optimizing the medium conditions without pH control. 49.2 grams per liter of 2,3-butanediol was produced at an initial pH of 8 under microaerobic conditions with the concentration of glycerol about 30 grams per liter. The addition of organic acids such as acetic acid and succinic acid has been demonstrated to be advantageous for the 2,3-butanediol production. The addition of succinic acid at 10 grams per liter to the medium containing xylose was found to improve 2,3-butanediol productivity from xylose by Cleblis oxytoca, but higher concentration of succinate were inhibitory. Then Nakashimada et al. Investigated the effect of organic acids on 2,3-butanediol production of Bacillus polymixa and found that 150 millimolar of acetate gave the highest 2,3-butanediol yield, that is 0.87 moles of 2,3-butanediol per mole of glucose, which is very good actually, and the concentration of 248 millimolar in a batch culture. When glucose and acetic acid were fed together in the ratio of 0.35 mole acetate per mole of glucose in the fed batch cultures, 2,3-butanediol production reached 637 millimolar and 566 millimolar at pH 6.8 and pH 6.3 respectively. Now, we will talk about the other one of the most important commodity chemicals, okay, PHA, that is polyhydroxyalkanonate. So, PHAs are a family of biopolyesters synthesized by many bacteria for energy and carbon storage purposes. The natural polymers can be melted and molded like petrochemical thermoplastics, but degraded completely into benign metabolic products by microorganisms in the environment. P3HB is the most common PHA. more than 100 hydroxy alkanoic acids have now been identified as the possible PHA monomers. They are usually 3 hydroxy alkanates with R configurations, resulting in high stereoregulatory and optical activity of the biopolyesters. The monomeric hydroxy alkanates can be roughly divided into 2 groups: short chain length hydroxy alkanates with 3 to 5 carbons and medium chain length hydroxy alkanates with 6 to 14 carbons. The size of side chain can to a great extent affect the material properties. Small side chains such as methyl and ethyl groups of HCl-P3HS result in a stiff material with high crystallinity, high tensile modulus and low ductility, whereas large side chains of MCl-P3HA make the material more elastic with lower crystallinity, low melting temperature as well as high ductility. So, the side chains actually the length of the side chains matters. Okay. So, controlling the size and content of the side chains in P3HA copolymers can therefore make a biopolyester with desired properties. So, basically you can tailor make a particular PHA. The material properties can also be modified by incorporating longer monomers such as 4 hydroxybutyrate and 4 hydroxy valerate in the PHA backbone. For instance, the 4HB content in a copolyester, okay, that is P3HB4HB increases, the crystallinity of the copolymer declines and its ductility increases. In microbial PHA biosynthesis, precursor of 4HB are supplied either as the sole carbon source or as a co-substrate of glucose. PHA biopolyesters, because of their biodegradability and biocompatibility, have attracted great research and industrial interest. They have been produced via microbial fermentation from various renewable feedstocks such as glucose, starch, sucrose, vegetable oils, animal fat and food processing residues. The production cost, however, is still relatively high in comparison with petrochemical plastics. It is attributed to the cost of raw materials, microbial fermentation and polymer recovery. Cellulosic biomass such as corn stubble and cane bagasse is a potentially inexpensive and renewable feedstock for bio-based fuels, chemicals as well as materials. Compared to starchy grains, cellulosic biomass contains much less glucan, more hemicellulose, lignin and other plant components. A substantial amount of organic residues are left from ethanol fermentation, posing a high treatment cost or environmentally liability to the biomass refining processes. A general PHA bioprocess consists of 3 basic operations. What are those? The first is the biomass pretreatment, second is the microbial synthesis and then third is the polyester recovery and purification step. Now, microbial synthesis of biopolyesters are complex and many times inhibitory substrates play a key role in the PHA bioprocess. Under controlled conditions, biopolyesters are accumulated inside the cell as inclusion bodies that may count for 60 to 80% of the dry cell mass. Glucose is a popular carbon source for PHA fermentation in laboratory as well as in industry. In a laboratory fat batch culture, a very high productivity of 4.6 gram P3HB per liter per hour and a high P3HB content of almost 88% was achieved. It is very significant report actually. The reference is given below, you can browse through it if you are interested to learn more. This high cell density culture, however, may be impossible in biomass refining because of a much lower glucose concentration and presence of other inhibitory substances in the feeding solution. Fat batch fermentation is a useful tool in controlling substrate inhibition for high cell density cultures. If you recall our discussions during fermentation, I have clearly told you how fat batch is an advantageous mode of operation with respect to batch operation, okay, or batch mode of fermentation. Okay. So, this is the classical schematic PHA biosynthesis from glucose, xylose and libunilic acidic route. So, let us understand glucose and xylose. Okay. So, both are giving acetic acid, right. So, xylose is giving an intermediate before it goes to acetic acid, xylulose. Okay. So, now this acetic acid is getting converted to 2-acetyl coenzyme A, then to acetoacetyl coenzyme N, then to 3-hydroxybutyryl coenzyme A, then poly 3HB, 3HB, 4HB, right. Okay. And you can see that this is the main metabolism pathway which is not been described here, been left out. Okay. So, this particular component is giving again to the 3-hydroxyvinyl coenzyme A, right, and from the libunilic acid also that particular step is getting in this going through 2 different intermediate compounds, and finally, we are getting poly 3HB, 3HB and 4HB as the product. Okay. Now, there are some intermediate steps which are been skipped here. This is just a simple understanding of the schematic biosynthesis pathway. The inhibitory compounds in hydrolysate solution, however, may not be utilized by microbial cells and could be accumulated with feeding, resulting in quick deterioration of the microbial activity. A continuous feeding system consisting of 2 bioreactors in series may provide a solution. So, how it can help us? Basically, in the first bioreactor you grow the cells, okay. The cells grow with a balanced nutrient supply, basically you are growing the biomass, okay. And in the second one PHA is formed under limited nutrient conditions at constant level of inhibitory compounds, because what happens when you are growing and producing PHA simultaneously in a single reactor, during the cell growth there are some inhibitory compounds production that actually inhibit the growth of the cell as well as inhibit the PHA formation. So, that will not happen if you are going to use a continuous feeding system having 2 separate bioreactors in series. For example, one system operated at a dilution rate of 0.08 hour produced 1.3 gram per P3HB per liter per hour with a yield of 0.36 gram P3HB per gram of glucose. The PHA content was 72% of the dry cell mass. Xylose is a predominant hemicellulosic sugar of biomass hydrolysates. Because of its poor utilization by yeast, it may also be a primary residual sugar in ethanol fermentation. An early study demonstrated P3HB accumulation on xylose and arabinose in Pseudomonas pseudoflava. In a well controlled bioreactor, the specific P3HB formation rate, cell yield and polymer yield on xylose were 0.03 grams per hour, 0.17 gram per gram and 0.04 gram per gram respectively, in comparison with 0.11 gram per hour, 0.36 gram per gram and 0.08 gram per gram respectively on glucose. 2 problems are encountered in the PHA biosynthesis on levulinic acid. The first is the acid toxicity and the second is the composition control of the copolyesters. With a strain of alkaligen species grown on levulinic acid and glucose, this PHA, that is P3HB3HB, was formed with about 40 mole percent of the 3HB. The cell growth of PHA synthesis were inhibited at a low concentration of levulinic acid, that is 1 grams per liter. So, this fact indicates that acid has a higher toxicity than propionic acid does, and a popular precursor substrate of the 3HB. A strain of Ralstonia eutropha, so formerly it is known as the alkaligens eutropha, was inhibited with levulinic acid at concentrations from 0.5 to 8 grams per liter. The copolyesters P3HB3HB formed on fructose and levulinic acid contains 35 mole percent of 3HB or lower. No 4HB is detected in the polyester backbone from its precursor levulinic acid. PHA with a high mole percentage of 4HB, almost 19 to 30%, could be synthesized on levulinic acid with a recombinant strain. So, the 2 references are very classical studies, particularly on the PHA formation, okay, from the levulinic acid. So, if you are interested to learn more, you can go through it. Okay. So, this table tells you about the monomer composition, average molecular weight, IR absorbance of the PHA formed on glucose, valeric acid as well as levulinic acid. Okay. So, 3 different carbon sources are given, their molecular weight, how much 3HB is getting formed. You can see from glucose it is 100%, okay. 3HB 0 3HV 0 4HB, okay. When you come to valeric acid, you see that 3HB is less, whereas 3HB, okay, is more, okay, and no 4HB. And when you talk about levulinic acid, there is a balanced formation of 3HB as well as 3HV, okay. So, although the average molecular weight of PHAs formed on 3 different carbon sources is quite similar, the monomeric composition varies. A homopolymer P3HB is formed on glucose. On valeric acid, a copolyester, okay, that is B3HB is formed with 3HB being the predominant monomer. You can see that 78.2 mole percent, okay, and 3HB is the only secondary monomer, or at least 22%. On levulinic acid, okay, this P3HB, 3HB, 4HB is formed, in which both 3HB and 3HB are the predominant monomers, while 4HV is a minor monomer. Okay. The IR absorption intensity at wavelength number around 1180 centimeter inverse is reversal to the crystallinity of the PHA matrix. The IR absorbance at wave number 1380 centimeter inverse is attributed to the vibration energy of methyl group of biopolyesters and often used as a reference. P3HB is a well known brittle PHA because of its high stereo regularity and high crystallinity, almost 60 to 70%. Its relative IR absorbance is 0.93, the smallest among all the 3 PHAs. The copolymer P3HB3HB has a lower crystallinity and a higher ductility than the P3HB does, but the effect of the second monomer on matrix crystallinity and material ductility is not high because of co-crystallization of the 3HB and 3HB. The terpolyester P3HB3HB4HB has the lowest crystallinity and highest relative IR absorbance because of the content of 3HB as well as the irregularity caused by the 4HB. Indeed, the cast film of this terpolyester exhibits a very high elongation at break, close to 500% in comparison with P3HB, which is less than 5%, and P3HB3HB, which is less than 50%. The melting point of the terpolyester is between 120 to 130 degree centigrade in comparison with the two other things, okay, like P3HB is 170 to 180, 3HB3HB is 150 to 160 degree centigrade, almost similar. Okay. So, in addition to glucose, xylose and levulinic acid, many organic hydrolysates exist in the solutions of biomass refining. They may not be primary carbon source because of relatively low concentrations, but can apply a great inhibitory effect on the PHA fermentation. For instance, Pseudomonas pseudoflava is able to grow and form P3HB on xylose and arabinose or the hydrolysates from hemicellulosic fraction of the poplar root. The strain, however, is inhibited completely in hydrolysate solution of high concentrations, almost greater than 30% volume by volume. The toxicity of hydrolysates depend on the 3 factors. First is cell density, then hydrolysates concentration and the inoculum preparation. A high initial cell density ranging from 3 to 6 gram per liter could effectively relieve the inhibitory effect of the hydrolysates. The hydrolysates and glucose are simultaneously utilized with cell growth and PHA formation. So, with this I wind up today's class and we are done with our discussion on commodity chemicals production from the biomass. Though biomass gives us so many different types of commodity chemicals, I have restricted our discussions to only those which are commercially being produced and are of high value. Okay. So, thank you very much. In case you have any query, register in the Swayam portal. You can always drop a mail at me to me at kmohanty@iitg.ac.in.